Good morning. This is your stats sensei, Mr. Spensei, and I'm going to be going over the review question, the take-home quiz questions, and I'll be making one video per. This will be the first question, which is scenario one, which is a 2005 question six. So regulations require that product labels and containers of food that are available for sale for the public accurately state the amount of food in those containers. Specifically, um, if milk containers are labeled to have 128 fluid ounces and the mean number of fluid ounces of milk in the containers is at least 128. So if it's measured, if say it has 128 fluid ounces, the average has to be greater than 128 ounces. So that matters because we're talking about the mean. The milk processor is considered to be in compliance with the regulations. The filling machines can be set to the labeled amount. Variability in the filling processes causes the actual contents of milk containers to be normally distributed. So they're telling us we have variability, but the distribution is normal. That's important. A random sample, so we have random sample of 12 containers of milk was drawn from the milk processing line in a plant, and the amount of milk in each container was recorded. So we know we have a sample size of 12, and we know it's normally distributed. All right. So the sample mean, so here we say sample mean and standard deviation. Well, this tells me I have an X bar of 127.2 and an S equal to 2.1. So standard deviation of sample of 2.1. Is there sufficient evidence? That's a key word. As soon as it says the word evidence, I know that I'm looking at a hypothesis test to conclude that the packaging plant is not in compliance. So let's be real careful about this. So first off, HO, the mean equals 128. Well, they know they have to have at least, the average has to be at least 128, greater than or equal to 128. But if it's less than 128, they're not in compliance. So that's what we're looking for, is whether or not it's less than 128 ounces. All right. So provide statistical justification for your work. Well, to speed this up, I've typed this up already. So very first thing we need to do is state our claim. Oops, wrong problem. So our claim, the mean is 128. We're in compliance if we're greater than or equal to 128. We're out of compliance as we're less than 128. So this would be our claim, less than 128. We always have to define our parameter. Let mu equal the true population mean number of ounces of milk in a container. I want to be real careful about this. If you go pull this question up online, it'll say, oh, we stated the conditions in a prompt, so we don't have to state them here. That would have been graded correctly in 2005, not now. Unless I say that conditions have been verified, then you have to give the conditions. So we have to give the conditions. Random sample of 12 was given, so we're good there. 12 divided by 1 or 12 times 10 is 120. It's reasonable to assume that there are at least 120 containers of milk. And the distribution of milk, we need to check the normality. Well, they already told us it was normal, which is really nice of them. So that's our given. So what we have here is we have a sample of milk, and our X bar is 127.2, but our population is supposed to be 128. So this is our claim. This is what the claim is, but we have 127.2. This is our X bar, and I'm basically looking for this area to the left. So we want the probability that X bar is less than 128. And we know it's a t-test because we're working with, they told us earlier that our standard deviation of the sample is 2.1 because we're working with standard deviation of the sample. That makes it an S, a t-test, as opposed to a Z. So t equals X bar minus mu S divided by the square root of n. We need to make sure that we remember to cross that out once we fill in our numbers. Well, our numbers are 127.2 is our X bar. Our population mean is 128. Our sample standard deviation is 2.1, and our sample size is 12. So here's where I go on the calculator. Stat, test, t-test. And we have a mean of 128. This X bar of 127.2. The standard deviation of 2.1. And a sample size of 12, and we're looking for a less than. Make sure that whatever you type on the calculator exactly matches what you have here in the alternative. And we end up getting T is negative 1.3196. And the probability of that is our p-value of 0.1068. All right. So our p-value is 1.1068. That's greater than an alpha of 0.05. So our decision is to fail to reject the null. So our p-value is 0.1068. We fail to reject the null. There is, make sure you have not sufficient evidence at alpha equal 0.05 to suggest the true population mean number of ounces of milk in a container is less than 128. All right. So that answers the question there, because basically we're saying, yeah, we have some evidence that it's less than 128 because our sample is certainly less than 128. But what we know is that could happen by random chance alone about 11% of the time, 10.68% of the time. All right, moving on to part B. Inspectors decide to study a particular filling machine within this plant. For this machine, the amount of milk in the containers has a mean of 128. So they're telling us this is what it actually has. So they're telling me the real mean is 128. And it has a standard deviation of 2. So they're telling me that the population mean is 2. Because I'm working with a population mean, this is a Z. When we're looking up here, we had the sample standard deviation. Sample standard deviation is a T, population standard deviation is a Z. All right, what is the probability a randomly selected container filled by this machine contains at least 125 ounces? A randomly selected machine. That tells me my sample size is 1. All right, so in this case, and then they say, what's the probability it has at least 125? So the probability X is greater than 125 is the probability of Z being greater than 125 minus 128 over my standard deviation of 2. Because essentially what we have here is this graph. We have a true mean of 128. But we want to know the probability that we get a single value X greater than 125. So we're actually looking for something that's going to be over 50%. All right, that's what we're looking for. Now there's a couple ways to go about doing this. So we could do second vars normal CDF, lower bound 125, upper bound positive infinity 9.99, mean of 128, and standard deviation of, what was our standard deviation? 2. And the great thing about that is, sure enough, I get my probability, which is 0.9331, but I don't get my Z-score. So what I would have done to get my Z-score and my probability, I would have gone stat, test, Z-test, and my mean happens to be 128. My standard deviation happens to be 2. My X bar, it's really an X, is 125, and it asks my sample size, which is 1. And I go calculate, and I end up getting 0.9331, but I also get the Z-score of negative 1.5, and it's really important that we have that as well. So the probability that it is greater, that we have at least 125 ounces from this machine is 0.9331. And that's like, oh, that's pretty good. 93% of the bottles will have at least 125 ounces of milk when the machine is at 128 with a standard deviation of 2. Then moving on to part C. It had to be Moses there in part C. And an inspector will randomly select 12 containers. So in this case, our sample size is 12. As nice as it tells random, are filled by this machine and record the amount of milk in each. So we're looking at the same machine, all right? What's the probability that the minimum, the smallest amount recorded in the 12 containers will be at least 125? So we have to have at least 125. And it says, note, in order for the machine to be at least 125, each of the 12 containers must contain at least 125. Now, I'm surprised they gave us that extra information. That was nice of them. But I want you to consider this. If we have 12 containers, we could have 0 that have 125, 1 that have at least 125, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have to have all 12 have to have at least 125. 0 containers having at least 125, not enough. 1, not enough. 2, not enough. I have to have at least 12. But really, what I need to do is I need to sit there and go 12 blanks. And the probability of having 125 is this, so I'd have it in there 20 to 12 times. Well, I can simplify that instead of writing 0.9331 times 0.9331, because that's the first bottle, second bottle, doing it 12 times. It's just 0.9331 to the 12th, and I end up getting 0.4356. So the likelihood that all 12 have at least 125 is 0.4356. And this would be adequate work right there. Okay. Of course, some statistician was a bit bored and we had to add more to this problem. An analyst wants to use a simulation to, sure they do, to investigate the sampling distribution of the minimum. That's interesting. This analyst randomly generates 150 samples, each consisting of 12 observations. So basically they're telling us our sample size is 12. We're going to repeat this 150 times from a normal distribution with a mean of 128. So in this case, they're telling us the population is 128 and a standard deviation of 2. Now this is all important information because they're telling us this is what, so we have a mean of 128, standard deviation 2, and finds the minimum for each sample. The 150 minimums sorted from smallest to largest are shown in the paper. Use the simulation results to estimate the probability that was requested in part C and compare this with the theoretical value. So when I flip over to the next sheet, I sit there and go, well, here's my list of simulations. And the smallest amount was 121. The largest amount that any of these had was 126. Now we're listing the minimum of 12. Well, in this case, we had 84 that were less than 125. And we had 150 of them. So 150 minus 84 equals 66. So based on the simulation, the probability that the amount of milk, or the minimum, the probability that the minimum was greater than 125 equals 66 over 150. And that's what I show over here. According to the simulation, it's we had the probability that it's less than 125 is 84 over 150. The probability is greater than 125, which is what we're interested in, was 150 minus 84, which is 66 over 150, and that equals 0.44. Well, really important, we have to compare to part C. All right. Well, in part C, we got 0.4356. Here we get 0.44. So theoretically, we should have gotten 0.4356, and we're off by a little bit. So the theoretical value is 0.4356, and that's very similar to our simulation value of 0.44. When I subtract them, I only find a 0.0044 difference between the two. Now, I want to be real careful about this. I should say that if you only gave me the computation, the 0.44, you got partial credit. So you went from full credit to half credit. Here's what was crazy. Running that entire hypothesis test was worth 1 point. They basically said you had 4 things that you had to have. If you had all 4 of those things, you got full credit. If you had, and that meant from the conclusion all the way up. Basically, part 1 was this. Part 2 was this. Part 3, the decision. Part 4, the conclusion. If you had all 4 of those parts, you received full credit. If you had 2 of those parts or 3 of those parts, you received half credit. Please remember that's a question 6 problem. And on a question 6 problem, we'd like to get you to get at least 2 of those FRQ points. All right, because all FRQs count as 4. However, question 6 is 25% of the score. Thanks for watching. I hope you'll stay tuned for the next one.